Okay, so for number 6, we have got f of x equals 1.02 e to the 3x minus 2. So, we got several things that we need to find here. It asks for an x-intercept and a y-intercept. So, in this particular case, you have both of those, and they're pretty simple to find. You're just going to click on it and look. It crosses the x-axis at 0.224. So, your x-intercept will be 0.2240, and the y-intercept is going to be at negative 0.09. Sorry, 0.98. There. And we're all right on those. Those in general, the only time those are hard to find is if they don't show up in the window well, or if they are like way far out on the edges or something, or super close where it looks like it doesn't touch. So those are not so bad. This one is an exponential. So we just talked about those exponentials. What is our domain for an exponential? It is all real numbers, or negative infinity to positive infinity, right? So that's the case anytime you have an exponential. It doesn't really look like that here, because if it's all real numbers, that means it's defined everywhere. Well, it looks like this has a vertical asymptote, like big time. It does. Because exponentials are so steep, sometimes they look like they have vertical asymptotes. But you can plug any number into this. You could plug in 1 gazillion into that for x, and it's going to give you a really huge, giant number that you probably won't even have a name for. But you can plug anything in. So domain for exponentials is always all real numbers. Our range, however, is restricted. So in this case, for our range, we're thinking about our y-axis. We're thinking about how far up or how far down we can go. So if we think about how far down this graph goes, it looks like it stops right here at negative 2. And if we put in a line at negative 2, when we put in the line at negative 2, and kind of look over here, you can see it never really drops below that negative 2. So we have a horizontal asymptote there. Negative 2 is the very lowest we're going to go on our y values. What's the highest? It is infinity. Because over here, on this side, it keeps going up, 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 up forever, right? So if you have the graph is shooting off the page where you can't see it anymore in a direction, you're going up in that direction forever. So that would be our positive infinity there. This and in behavior are the only two times that we're thinking about up or down, right? Every other time we report the x values, but here we're talking about from here up to positive infinity on the y-axis. Okay, we're okay here. All right, let's see what it asks for next. Next, it asks for vertical asymptote. We do not have a vertical asymptote. Exponentials do not have vertical asymptotes. Their domain is negative infinity to positive infinity. There's no vertical asymptote here, even though it kind of looks like it, because that is so steep, it kind of looks like it is getting closer and closer and closer to a line. But if we, I'm going to zoom in a little, so like, if we saw this, it looks kind of like maybe 1 is the vertical asymptote here. So if we put in x equals 1, that looks a lot like a vertical asymptote, actually. But if you go up here, eventually it does cross that line and go to the other side. Be careful with just looking at the graph, though, because sometimes it is so steep that it's going to look like it's a vertical asymptote, and you kind of like reach the limits of your technology. We do not have a vertical asymptote, so our vertical asymptote, that will be none. But we do have a horizontal asymptote, and that horizontal asymptote is this purple line that we have right here, right? It's going to get closer and closer and closer to that line. Horizontal lines are y equals, and in this case, y equals -2. It said +2. All these 2's were negative, should be -2's, but they all say +2 on the key, so that's wrong. There. So, we're all right up to this point. All right, so increasing and decreasing, it's either always increasing or always decreasing on the domain. So in this particular case, if we're going from the left side to the right side, which one is this doing, increasing or decreasing? It's increasing. So we're going to be increasing for the domain. So whatever, that's why domain is like, domain and range are the ones I really care the most about, because domain is so important because it's answered a lot of other problems also. So it's increasing everywhere, and everywhere for this function is -infinity to +infinity. So whatever the domain is, that is what goes here for increasing, because this one is always increasing, which its domain is -infinity to infinity here. It will never decrease, so it'll be, for decreasing, you'll have none. There. So, positive and negative are a little bit difficult to do, I feel like. So, when we're talking about positive and negative, right here, at that point right there, at that x-intercept, that's when we cross the x-axis. Before that, over here, we are below the x-axis. That means we're negative. And then here, we're going to be positive. So, the domain for this function is -infinity to +infinity. It's defined everywhere. Right? So, this graph exists all the way down here at -infinity. And from here all the way up to that point right there, it is below the x-axis. So that means it is negative. So for, well, they write positive first. All right. So I would have -infinity up to 0.224. That is when my graph is below the x-axis. I'm given the x-coordinates of all those points, right? Is what's happening here. Not the y. It might seem like it should be -2 to this, but you're not talking about the y-coordinates. You're talking about the x-coordinates. On that x-axis, it's -infinity up to this point. And then so it is positive the rest of the time. So from 0.224 up to, this keeps on going to infinity, our graph would be positive. So positive and negative, you're thinking above or below the x-axis. Okay, questions on that part? All right, and then we've got concavity. Concavity is a lot like increasing or decreasing. So concave up and concave down. So concave up or down, it's going to be the same for the whole function for these functions, for exponentials and logs. Which one is this? Concave up or down? is up. It's curved up. So, again, this is another case where it's concave up for its entire domain. So our domain is just going to go here for negative infinity to positive infinity. All right, and then it will never be concave down. And then on that last part, oops, we've got as x approaches blank, f of x approaches blank, and then it says it again, as x approaches blank, f of x approaches blank. So this is your end behavior stuff. So whenever we're doing these problems, again, we're pulling from the domain. So think of this as your left-hand side of the graph, and this is your right-hand side of the graph. So what we do is we take the left point of the domain, which for this one is negative infinity. It goes right here. And we're going to take the right-hand point of the domain, and it's going to go right here. So we're going to have as x approaches negative infinity and as x approaches positive infinity. So on the left-hand side of the graph, if I start somewhere here in the middle and I go to the left, this is, again, one of the only times we're looking at our y values. What is our y value approaching or getting closer and closer and closer to? Is it going down to negative infinity, or is it leveling out? Leveling out, right? Where's it leveling out at? Negative 2, right? It never goes below negative 2. It just gets closer and closer and closer to negative 2 on this left-hand side. So you're thinking about y values for this part. So that would be negative 2 there. It has a positive 2 on the key, but that's wrong. And then on the right-hand side, if you start somewhere here in the middle, anywhere in the middle, it doesn't matter, and you go to the right, what's happening to your y values here? They're going up, 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 up. It's positive infinity. Hello? The first type of problem that we're going to look at is going to be just your basic exponential growth formula, which is y equals a times b to the x power. So a is your principal or your starting value, so whatever you start with, and b is your growth or decay factor. So for your growth or decay factor, if you have exponential growth, you're going to take 1 and you're going to add whatever the rate is as a decimal. If you have decay, you're going to take 1 and you're going to subtract whatever the rate is as a decimal. So one thing I sometimes do to like help you guys like think of this, like if you buy something that costs $20 and there's 7% sales tax, right? How do we figure out how much you owe in total there? What's the quickest way we could figure out what you owe? Good. We can multiply by 1.07 because what you're doing there is you have to pay 100% of the price plus an extra 7% that you must give to the government for a total of 107% of the price, right? Which as a decimal is 1.07. So if you want to figure up sales tax really quickly, if it costs $20, you just do 20 times 1.07. And it would give you the total amount that you owe. You don't have to figure sales tax separately. It just adds it back in, right? So same thing is going to be the case when we're doing these exponentials. If we have 1.07, that's a growth rate of 7, right? What about if we have a discount? Let's say that we buy something that costs $20 and it is 30% off, right? What would be the quickest way? You could probably maybe like do it in your head. Let's say it's $27.99, right? And we want to know exact. So if it's $27.99, and we want to know exactly how much we owe, what would be the quickest way to figure out how to get the or get what you got to pay if it's 30% off. Multiply by 0.7, right? Because what happens with a discount is you always start from 100, which is what this 1 right here is for these. And you would have to subtract the 30% that they're taking away from the price. So a lot of times when I'm doing this in Math 1, I'll tell them if it's 30% off, that means it's 70% on. You got to pay 70% of the price. So you just do 27.99 times 0.7. That would give you the amount that you owe. This value is going to be less than 27.99. On these, always make sure your answer is sounding reasonable. Because sometimes when I do this, I get students, I tell you, I always do like a review of percentages in Math 1 before we go into exponentials. And I tell you, if you want to rip off a group of people, there's some targets in my Math 1 class, because sometimes you'll tell them that a shirt costs $27.99, it's 30% off, sales tax is 7%, how much does it cost? Sometimes I get answers like $127.30. And clearly that has to be wrong, right? Because it was on sale. It can't cost more than 20, and sales tax is not more than the discount. So it can't cost more than $27.99, but they'll get crazy stuff and then they won't question themselves. So that's something I try to teach them to do as we work along. So make sure you're also doing that here. I was insulted yesterday because we weren't doing percentages, but I had a student working on a problem that I made up that was like my sister is 2 years older than I am. 2 times my age plus 4 times my sister's age equals something. We're doing systems of equations. And they were supposed to solve it. And it was going to tell them how old I was. And one kid got 80. And he did not question whether or not he was right when he got 80. And I told him that I didn't look quite that bad. I might not look younger than I am. I might look older, but not that much older. So just make sure that whatever you're getting seems reasonable for the situation. Now, sometimes with exponential growth, that's a little hard to do. Because another thing that I sometimes do in Math 1, and Miss Ball might have, you guys are Miss Ball's math students, right? I know you were Miss Ball's math student because she's been teaching you math since you were a baby. But I sometimes forget where the cutoff was, where she went down to the 8th grade. But I'm pretty sure everybody now had her in the 8th grade that I have up here. I don't think. Has she been down there 4 years? Seniors had it. Okay, you guys had it first. Yeah, so everybody here, unless they failed a grade, had Miss Ball in 8th grade. We're doing some exponentials today. I was telling them to make sure their answer makes sense. We was doing a problem yesterday in Math 1 about how old I was, and the kid got 80. And they didn't question whether or not they were right or not. I told them I was insulted. Yeah, it could be. So whenever, so where was that? Coach Woods messed me up. You guys all had this ball. So it's been 4 years. Five. This is our 5th year down there. So whenever we go over this, for these problems, what I just want us to do is look about whether it's growth or decay and by what percent. So when it's growth or decay and by what percent, we're looking at that B value, the value that's being raised to the exponent. So for number 1, Maddox, is that going to be growth or decay? It is growth. And I know that because 1.05 is bigger than 1. So it means we took 1 and we added something to it, right? What percent is it growing by? It is growing by 5%. Because if I take that 1.05, I subtract the 1, I get 0.05. And if I move my decimal 2 places, that's 5%. All right, second one. Connor, what do you think? Growth or decay? It is growth. I know that because this number that I'm raising to the exponent is bigger than 1. What percent? It is 200%. Very good. Those are tricky sometimes, the whole numbers. So it's still like tripling. So whatever value you have is tripling. But tripling is 200% growth. You take the 3, you subtract the 100% you started with, which gives you 2, and then you move that decimal place 2 places, so it's 200%. So like if something is quadrupling, it would be a 300% growth rate. Or if it's being multiplied by 10, it would be a 900% growth rate. Which I think is probably something we could all do a little better to understand, because it's been driving me crazy, especially lately with COVID numbers. Well, when I say lately, I mean the whole last 2 years. COVID numbers they give you percentages a lot of times of growth or decrease, which are fine and sometimes helpful, but not helpful if the numbers are low. Like child hospitalizations are up 50%. That could mean that they went from 2,000 to 3,000, or it could mean they went from 2 to 3, right? 2 to 3 is not concerning whenever we're talking about a world consensus. 2,000 to 3,000, a little more concerning. So it would be good for us to all understand this a little more. All right, for number 3, Noelle, have we got growth or decay? Decay by what percent? It is 2%. Very good. There. So you got 0.98. If you subtract that 1, you're going to get negative 0.02. The negative tells you it's decay. 0.02 would be 2%. The biggest mistake I see students make here is they say that's 98%, because they just change it to a percent. But you got to think about how far away is it from 1. Subtract it from 1 first. So that's good. All right. And then Reese, what about number 4? Is that growth or decay? Is decay. What percent? 50%. Good. Okay, any questions here? You guys remember doing this? I know you would have done it with Miss Ball. You guys had Miss Ball normal, regular class. No excuses. I'm just waiting for Hunter's class to get up here, because Hunter's class was in 3rd grade whenever the shutdown began. And I feel like I'm still going to be seeing kids in his class claim that they don't know their multiplication tables because they missed the last half of 3rd grade. I feel like it's happening. It's coming. All right. So, there's a legitimate online school, not as good, but at some point you have to catch back up. That's what we're working on now. We're going to do fine. All right. So, compounded interest is something that is really important to know about, and can be applied in a lot of financial situations. So our most typical math problem compounded interest is usually compounded annually. And the reason that you see that more often is because right here I've got 5% APR, which is your annual percentage rate. All right, so if you see APR, that's your annual percentage rate. If you are looking at a worksheet that I have done and it doesn't say APR behind it, just go ahead and assume I meant APR, because I probably did. Unless I say something different. I probably meant APR and forgot to put it there. So if I have an annual percentage rate of 5 and I'm compounding annually, then I do not have to do anything special for this problem, right? So if I invest $6,000 in an account earning 5%, compounded annually, I want to know how much money I have after 5 years. So all I have to do for this is I have to do 6,000, which is my initial amount. I'm going to multiply it by for this growth rate, if I have 5% growth, it's 1.05. Taking 100%, adding 5%, it's 105. Move your decimal 2 places. And then I'm going to raise this to the 5th power. That exponent is always your time. Now, your percentage rate time and your time you're plugging in have to match. So I've got annual percentage rate. I'm plugging in years. So that's fine here. And so if I type that in, some of you already typed it in, what do we get? Okay. So $7,657.68. Okay, so the way that we do the second part, there is a formula that I can teach you, and I can show it to you if you guys are really formula people. But the reason I don't like the formula is because I find that nobody ever remembers the formula. And so if you don't remember the formula, it doesn't help you be able to do these problems. So I don't use the formula. I do use the formula because my logic is the formula. But instead, I just remember this. So let's say we've got the exact same situation, same amount of money, same interest rate, but instead of compounding annually, we're going to compound monthly. Okay? So that means we have to adjust our interest rate and our time to be in months instead of in years. So our initial amount is going to stay the same. We got $6,000. My interest rate, so annual interest is 5%. My monthly interest, though, has to be adjusted because they're not going to give you 5% every month. That was like, if you ever find a bank that's going to give you 5% every month, you need to put all of your money there quickly because you're going to be rich. But you're not going to find it because it's going to be an incredible amount. So if you have a 5% annual interest rate, we need to adjust that to be monthly, so we're going to divide it by 12, right? Because there's 12 months in a year. So if we take 5 and divide it by 12, what do you guys get whenever you do that? 416 repeating percent. So our number that we're going to use here, it does get a little tricky with this because that is a percent. It has a decimal in it, but it's a percent. So if I change this to a decimal, it's 0.00416 repeating. All right. So my number I'm going to use here is 1.00416 repeating. And then I cannot raise this to 5 here because that would be 5 years, but this equation takes months, right? So if I put 5 there, it's going to be like I've only looked at 5 months. So what should I plug in instead of 5? I'm going to plug in 60 because 5 years equals 60 months. I just multiply by 12 there. So you have to adjust your rate and you have to adjust your time so that they're both in terms of months instead of years. And of course, you'll do the same thing but differently if you have quarterly, if you have daily, if you have weekly, all those things. So if we type that into the calculator, somebody tell me what we get for that. Somebody got that one for me. We are. Well, it's not till April, so hopefully we'll be back by then. You'll be fine. You'll be able to be there. That's going to last till April 23rd. You can feel it coming on already. In a few months it'll be here. We are having hopefully. We have got a place to have promise. Alright, so what did you say, Connor, before we were rudely interrupted? 100.152. Yeah, we'll just go. Huh? Okay, yeah. Alright, so and this is going to give us a little bit more money. So if you ever have the option between being compounded more frequently or less frequently, at the same rate, you want to go with more frequently. It's going to give you a little more money. It's not groundbreaking here. You're not going to go on a shopping spree with what extra you've got here, but you might could go out to eat, right? It gives you a little bit more. Okay? Questions on that? All right, so this time Alfredo is going to invest money in an account that gets 4.8% interest, annual interest, compounded quarterly. How long will it take his money to double? I love this problem because it seems to be missing so much, doesn't it? What are we missing? We're missing the baseline, what he starts out with. I don't know how much money Alfredo has. I don't know if he has $1 or $1 million. Probably somewhere in between there, but I don't know, right? So I want everybody to just make up a number. So don't tell your neighbor what number you made up. I want everybody to have a different number. Make up a number for your initial amount. So however much money you think Alfredo has. I think this is about Alfredo, who is senior, so he might be making the big bucks at Walmart there, so he might have a lot, I don't know. They do get paid pretty well. I mean, that is for a part-time as a teenager job.
You just said it's like so.
Yeah.
Probably.
Yeah. So probably not easy, but that is pretty good money for a part-time job as a teenager when you don't have a house and bills and all the other things to pay for. So. And a service that I greatly appreciate, because dragging 2 kids into the grocery store, I don't even know how I did it for all those years. But I don't want to go back. Okay, let's look at what everybody's getting here. So I made up the number of $541. So if Alfredo has $541, then if I double it, then he should end up with $1,082. Right? And so I had to adjust the interest rate by dividing it by 4, because there's 4 quarters in a year. So that gave me 1.012 here, because I just did 4.8. Divided by 4, which gave me 1.2, and then I need to move that decimal 2 places, so it's 0.012, and then put the 1 in front of it. Here. And I made myself a note over here that when I get my answer, that X is the number of quarters that I have, not the number of years. Or if you want to use a number of years, you can put a 4x up there if you prefer to do that. But I usually just remind myself that it is quarters. So, if I want to solve this, I got to divide by 541. So I divided by 541. I want you to have a different amount of money. But when you do your first step of solving this equation, what do you have? Do you have the same thing I've got on this next line? You should, right? So did it matter how much money he started with? No, it did not matter because time to double is going to be the same. So, so at this point, what am I going to do to solve now? The x is in the exponent. This is where our logs come in. So here's where we differ from what we were doing in Math 1. In Math 1, I would have had to graph it on the calculator or something was the best we could do to solve this. But we know how to solve it now because we know how to do logs. If I have a base raised to an exponent, the log with that base gets rid of it, right? So I'm going to do log with a base of 1.012 on both sides. It will cancel the exponent here, so I'll have log of 1.012 of 2 will equal my x here, and let me get the calculator real quick. So change of base, we'll just do log of 2 divided by log of 1.012. And we get 58.108. So x equals 58.108. Now I wanted to say years there. Is this years? This is quarters. Right? So this is quarters. How do I change it from quarters to years? Because if I ask you a question like, how old are you? And you tell me something like 68 quarter years old, I'm going to think you're insane, right? That would be a really strange way to answer the question. It might be correct, but it's going to be weird. Like on grown-ups, whenever they ask how old the little kid is, and he's 48 months. So it's odd, right? Past a year anyway, it's odd. So what do I need to do here to change it to years? Divide it by 4. And so if we divide it by 4, we're going to get 14.527 years. And this is exactly the way your compounded interest, or any interest that's compounded at any amount, not just quarterly, but at any amount, is going to work for you. It didn't matter if Alfredo put $1 in this account and left it for 14.527 years, then he would have $2 after that amount of time, right? That wouldn't be very much. But if he had $1 million, that means after 14.527 years, he would have $2 million. It's the same percent increase, right? That's why I say that whenever they give you percent increases on coronavirus numbers without giving you the numbers, that it may or may not really matter. Now, like right now, they're through the roof, so it probably does matter because they're huge numbers. But like over the summer, oh no, Delaware's up 20%. Well, they only had 17 cases the day before. You know, it's not really that big a deal when you're at really low numbers. So it's the same thing here. It's that it's the percent, the proportion of it's the same, going from $1 to $2. But when we're talking about usefulness, 1 million to 2 million is way different, right? So, and this is why the rich get richer, because if you put lots of money in an account and let it sit there, it goes up, up, up. But, now I will say right now, I think my savings account is getting like 0.1% or something, so you can't sit anything in the savings account right now. You have to put something in like a riskier account to make any money on it. So you can lose money in those accounts. So it could go bad. Right now, things are going up. But I don't know how long that's going to last because it's kind of volatile right now. But so let's talk about continuous growth and decay. We don't have time to watch it today, but tomorrow at the beginning of class, I want us to watch a video about E. It's like a 10-minute video that I want us to watch because it does a really good job of explaining E and like the different where it comes from and the different places that you see it. But E is used for continuous growth. So, for example, if we go back to that $6,000 for the first problem, if we compounded it monthly, we had a little bit more money, right? If we compounded it weekly, we'd have even more money. If we compounded it daily, we would have even more money. If we compounded it every second, it'd give us even more money, even though it's going to be tiny increments it's increasing. It's not like you're going to have millions more. If we could possibly compound it continuously all the time, then that would be our ideal situation. And so it'll show you tomorrow, but whenever you go through that process, and it's sort of like a calculus concept, thinking of that getting larger and larger number of times it's compounded, you get to this formula, A equals PE to the RT, which is our continuous growth or decay formula. This PE to the RT, sometimes I'll call it the PERT formula. I tell you, I'm getting so old because I have found myself just in the last several days telling kids about how it was back whenever I was young. When I was young, there was all kinds of commercials on TV for the PERT shampoo. I wonder if they even make PERT shampoo anymore. Shampoo and conditioner in one. It was revolutionary that you could get shampoo and conditioner together. So we were all very familiar with PERT, but for you guys, it's just like a silly word that somebody came up with maybe. But there was PERT shampoo. It was very good. Slight side note, have you noticed that women's products, they give you like 1,000 different products, like you got shampoo and you got conditioner and you might have like this leave-in spray and you got hairspray and you got maybe some sort of hair mask, or all, they try to sell you as many things as they can for you to wash your hair with. But for guys, it is the exact opposite. They are going to buy the bottle that says it is body wash, shampoo, conditioner, toothpaste, all in one, right? You can use this to clean any part of your body you want. And a guy's going to see that on the shelf and they're like, that is what I need. No need for all these bottles. Meanwhile, you have to buy like entire caddies to keep all of the female products. What is happening is they're playing us here. Is we may not actually need all of that, but they're getting us to buy it all. For some of us. I don't know. Shampoo and conditioner one does not work as good. It's good. I think I need my separate ones. All right, so rate is your R as a decimal. As a decimal, but not added to 1. You don't add it to 1 here. That part is incorporated in this E, and then T is your time. All right, so Walter just got a job as a high school chemistry teacher. His first year, he lives with his parents, and he saves $20,000. He puts the money in an account that earns 6.75% interest compounded continuously. If he leaves the money in the account without making any deposits or withdrawals, how much money will be in the account when he retires 29 years from now? So let's say that this happens. Our initial amount would be $20,000. It is compounded continuously. So we are using the PE to the RT formula. So we're going to have E to the R is our rate, but we need to change it to a decimal. So it's going to be 0.0675. And we've got 29 years. And here's an example of where I always forget to put APR behind percents. If I don't put a APR behind something, assume that's what I meant there. So that's our annual rate. We are plugging in years, which is going to be the case with continuous stuff that we're going to be doing. In most situations, especially at least interest here. And so we'll plug in our 29 here. So if this were the case, did I need parentheses? I think I did. That's not the right answer. Hold on. I needed parentheses because that whole thing is in the exponent. So 20,000 e to the, let's do some parentheses, 0.0675 times 29. That's better. That's the answer. So we get, he would have $141,632, and let's round that to cents because we're talking about money, so 2 cents. So if you could possibly, your very first year of working, save a pretty good amount of money here, and put it in an account that is going to grow, put it in whatever retirement or whatever. 6.75, that's a pretty good interest rate, but still, over time, you got a lot of money from that. And this is if he just only saves money that very first year and doesn't save any money the rest of the time. Ideally, you would save money every year. But anybody that is telling you to do retirement planning stuff is going to tell you to try to save money early because that money has more time to grow. The problem is unless your parents are really funding your college education well and giving you lots of spending money, if you're like myself, you went through college without a lot of spending money, then you finally get a job and it seems like you're making like tons of money because you've never had a real job before, and then you get your first paycheck and you do things like go buy a TV or a new car. Which my husband and I did both of those things. I think my husband we bought a new TV with his very first paycheck because he started in May. I didn't start until August because I, was a teacher. We bought the new car before I even got my first paycheck. It wasn't a fancy new car. It was like a Corolla, but still. These were not our greatest financial decisions because we could have made do with what we had, but it was, exciting to get new cars and TVs. So, but don't go overboard with that. We didn't go overboard. It's not like I went out and bought like a $80,000 vehicle or anything. It was a Corolla, but we still did go do all those things. So be smart with your money. Don't blow it all. No matter. I will still say I should not have bought that new car. Financially, it's not like it was that big a deal. We paid for it. We paid it off in 3 years, and it was fine. And it was a good car, and it was not a horrible decision. But I could have kept driving what I had. I didn't have to get a new car right then, and saving some more money those first few years would have been good. Because then, when you buy a house and you have children, then all that money you were making, you're like, oh, I've got so much money, new cars, TVs, this is great. Suddenly you're like, where's all that money at? I thought seemed like a lot of money to me. This is not a lot of money at all. What has happened? That definitely happened to me whenever we bought a house and had kids. So, I would have liked to have that. Well, I wouldn't be at that point yet. But, okay. All right. All right, let's do this one, because this one is a little bit different on how we're going to do this problem. So, Jeffrey has $4,000 in an account that gets 5% APR compounded continuously. If he does not make any deposits or withdrawals, how long will it take him to have $10,000? So, this is a different type of a problem because the question's asking how long, not how much is he going to have. So we're going to have 4,000 e to the rate is 5, so that's going to be 0.05. And t, we don't know. That's our variable. Right? We want to know when this will equal 10,000. So over here, we're going to put 10,000. And so, let's see. Noelle, help me with this. How am I going to solve that equation? I cannot do 4,000 times e. And the reason is the order of operations. So when I'm doing order of operations, I have to do exponents before I can multiply. So these exponents right here, I would have to deal with it before I could multiply anything together. And I can't do that because one of them is a t. So it seems like I should be able to do that, but I cannot. But I'm glad you said that, so now we know we cannot. So we're trying to get this t by itself, but it's all the way up here in the exponent, right? So before we can get the t by itself, we got to get the e by itself, which means we got to get rid of that 4,000. So I can divide both sides by 4,000. And that is going to be 10 divided by 4 is going to be 2.5 equals e to the 0.05 t. So once we've done that, what could we do now? We're trying to get to that t. The e needs to be gotten rid of. How do we get rid of it, Noelle? Good, natural log. So we're going to natural log this side. It's going to get rid of our e. Natural log this side. So natural log of 2.5 is going to give us 0.91629 equals 0.05 to the t, or times t, sorry. And then what would our very last step be, Noelle? Very good. It's going to be like 5 multiplied by 20. So 18.326. And that would be in years. If only you could get 5% in a nice safe savings account these days, that would be great. All right, and we finished up just in time. So your assignment tonight is going to come from this worksheet, but it's not the whole worksheet because we still have some other types of problems that we're going to do. So, I want to say, what's your 6 and what's your 8? I have to look it up. In general, I tried to put the word continuously in the problem if you need to use the PE to the RT formula. I don't know if it'll matter too much today. Today it's much more than math. Sometimes it will matter in the future. Let's see here. So homework tonight is going to be just number 1 through 6 on the worksheet. So the rest of the worksheet is going to be homework tomorrow. So I know math is exciting and you might get carried away, but try to, I mean, if you really want to do the rest of it, you can, but then you will not have anything to do at the end of class tomorrow.